Okay, good everyone. Now, let's look at series and parallel connection of semiconductor devices. Now, why do we need to connect these devices in series or in parallel? Now, if I have this in series like that, what do I need to do? What am I doing? I just want to make sure that I increase the peak inverse voltage rating. For instance, for this diode. Remember, if this diode, let's assume that I have a diode with peak inverse voltage of, let's say, 200 volts. All right. Let's just make it 400 volts. So I have these are 230 volts. Put my load there. All right, the output here will look like that. Forward biased. When it is reverse biased, it blocks off. Okay. On reverse, this is voltage, but the peak inverse voltage here is 400 volts. Look at the source voltage. So you can't break down this. Okay, so you get like that. But if you make a mistake and change this to 600 volts, or even 415, let's say 415 volts, for instance, you are not going to get this anymore. You will just get that, because of forward, okay, current will flow. Reverse, this is more than that, more than the peak inverse voltage, so it will break it down. So, but if I now take the same kind of diode and put that in series, okay, so peak inverse of 400 here and peak inverse of 400 here, that will give you total of 800 volts peak inverse. So this therefore cannot break down that, so you get something like that. Okay, so we really need to connect these things in series when we want to increase the peak inverse voltage. So now thyristors in series, switch on characteristics may differ. Okay, forward leakage current and switch off characteristics may also differ. All right. Now, so if you have something like this, we'll have a thyristor in series. Let's assume that they have all their respective snubber resistances. Okay, and then just as shown, to protect also the thyristor from transient voltage. Right, so we can now see that the voltage across each of the diodes, let's say it's VD1 for the diode 1, VD2 for the diode 2, and the VDN for the diode N, the last one. Okay, so we can easily write this equation, and maximum steady state voltage we can write in this form, assuming all thyristors are the same, you know, except the first one, T1. Okay, we should know that when current gets in there, IT1 gets in there, it can divide into 3. So now, assuming that all thyristors are the same except T1, then ID1 will be less than ID2. If you check the current flowing through D1 will be less than that flowing through D2, because when IT1, so ID1 will be less than that of ID2 if transistor 1 or thyristor 1 is not the same thing with that of 2 and 3 until the nth one. Okay, so and which ID2 equals ID3 equals ID4 to IDN. But just the ID1 that is not, because of because the other thyristors are the same except the thyristor 1. So maximum voltage across thyristor 1, which is the one that is different, thyristor 1, the maximum voltage across thyristor 1, okay, we can write that as VD1, which is Vs minus Ns minus 1 times the resistance times the change in current flowing through the diodes divided by Ns. So where Vs is our total voltage, now the total voltage from VD1 to VD2 to VD until VDN. Okay? And then Ns is the number of thyristors in series, and delta ID is the difference between the current flowing through the diode 2 and diode 1. Okay, because diode 2 and diode 1, the current is not the same, because the diode 1 and diode 2 are two different things. Okay, in this case. All right, so then the worst case scenario is that ID1 is 0. So thus for steady state, we can easily write that the VDS maximum is Vs plus Ns minus 1 by R times ID2 divided by Ns. And we can also include derivative factor. And the derivative factor will give you 1 minus Vs all over Ns VDS maximum. Okay, you can convert that to a percentage. All right, and then the voltage difference between, because of difference in reverse recovery charge, delta V is the same thing as delta Q over C1. Remember that CV equals to Q. So if I want to get V, I can just get the V changing Q over C1. Okay, while changing Q is Q2 minus Q1. If we're looking at the charges on the capacitors, all right, that we got here for each of the capacitors, the charges when the switch is on, when the switch is off, when any one of the switches, all right, is off, then so assuming again that all thyristors are the same except T1, so we can still write that Q1 is less than Q2, but the rest, Q2 equal Q3 until equal Qn. And worst case scenario, we can still write Q1 to be 0. So for transient, we can easily write that Vt of the transistor maximum, or VD of the transistor maximum, is 1 over Ns into Vs plus Ns minus 1 by Q2 over C1. And we can also have the derivative factor as 1 minus Vs over Ns VDT maximum. Okay? So this, if you check an example, it's just an example from Rashid. It's 10 thyristors in series with 15 kV, which can withstand 15 kV. And maximum change in diode current is 10 milliamps, and the change in quantity of electricity is 150 microcoulomb. Now, the sharing resistance is 56 kilo ohms. E1 is 0.5. We also calculate the steady state VDS maximum and the transient VDT maximum, and also calculate the steady state derivative factor and transient derivative factor. So you just try to get the formulas. So the first one, the steady state transient, the steady state voltage across the diode is Vs plus Ns minus 1 by Rd ID2 over NS. So the source voltage, in this case, is given, have 15,000, right? Okay, so now there are about 10 thyristors, okay, and they can withstand 15 kilovolts. So that peak inverse voltage about 15,000. So 15,000 plus 10 minus 1 times 56 times 10 to the power 3 times 10 to the power minus 3 times 10 times 10 to the power minus 3 divided by 10, that gives you 204 volts. Okay, 2004 volts. Then you can now calculate the derivative factor. That's 25.15%. To get that. Now, let's look at the next one. If you want to connect this in series, what do you want to do? I mean, in parallel, right? If I have these diodes and that diode in parallel, okay, remember that this has a current rating, let's say it's 20 amps, and this is 20 amps. It means that this can take care of 40 amps. Okay, so if you make a mistake and this is not there, current flowing through here is 20 amps, and this is 40 amps, and this is 20 amps, you are going to destroy that diode. So when you want your system to carry more power or more current, right, you put them in parallel. All right. So now, thyristors, or diodes, or transistors. On steady state, we use resistors in series, and transient, we use coupled inductors. So now, if I have the two thyristors to be connected in parallel, all right, remember, we still need to protect them, protect the switch from the IDT. So that's why you're going to have resistance, an inductance L, all right, attached to in series with each of the switch or thyristor. So, BJT, negative temperature coefficient, MOSFET, positive temperature coefficient. All right. Okay, easier method, you mount on a common heat sink. All right.